So in the last lecture, we talked about forces and Newton's laws. We talked about the first law, which told us about inertia and mass. We talked about the second law that related the forces acting on an object with that object's acceleration. And we talked about the third law, which says that for every applied force, there is an equally strong opposing force being applied in the opposite direction. Then I showed you all some examples of force problems where we broke the forces down into their x and y components and then solved for whatever we needed to solve for. And then we finished off the lecture by talking about the force of gravity and weight of an object and how we calculate both of those things. Now, in today's lecture, we will go a bit more in depth with some forces we will most likely encounter in problems that use forces. So we're going to talk about normal forces. We're going to talk about free body diagrams, apparent weights, the two different types of frictional forces, static and kinetic. And we're also going to be talking about the forces of tension. So we're going to finish up today's lecture by talking about two different types of overall force problems: equilibrium force problems and non-equilibrium force problems. So knowing which of these two types of situations we're dealing with will be very helpful as we solve problems later on in this course. But we'll get to all of those later in this lecture. So for now, don't worry about it. To begin with, we're going to begin talking about normal forces. So the normal force. So the normal force, not like your average everyday force, but more specifically the force that is normal to the surface or perpendicular to the surface of an object, is denoted by F sub n. Right, so F sub normal. And it is one component of the force, is one component of the force that a surface exerts on an object, that a surface exerts on an object, with which it is in contact, with which it is in, call it direct contact, comma, namely the component that is perpendicular to the surface. So that was kind of referring to what I said earlier. So namely the component that is perpendicular, to the surface. Right. So now I'm going to show a brief example. So first I got to draw a table. So we got one of these, maybe one of these. All right, this will be our tabletop. It looks kind of good. We have the table legs. Look like that. Maybe there's another one back here or something. Right. And let's say there's a book sitting on top of this table. So I got to draw another box here. So please forgive my drawing skills. But we got this book. It's sitting on this table. So right now, for our purposes, there's two forces being exerted on this book. So the first force is our normal force, which is the table pressing upwards on the book. That's our normal force. And then we also have the weight of the book pulling down, right? Because we're saying that down is toward the center of the earth and our weight points downwards towards the center of the earth. So the weight is given by the mass of the book times the acceleration due to gravity g. And so these are the two forces that are being exerted on the book. So as we can see from my amazingly lifelike drawing, that the book is making contact with the table. As a result, the table exerts a force on the book perpendicular to the face of the table, right? That is this normal force here. In this case, the normal force pushes upwards on the book. The book itself has a mass and is existing in a gravitational field, so it has a weight, which is pulling down on the book, which is pulling the book down onto the table with a magnitude of mg, like I said here. But there's really two objects in the drawing that I've made, right? I've drawn a book, right? But I've also drawn the table. So we can examine the forces on each using free body diagrams, which I mentioned very briefly in our last lecture. So here we can see all the forces acting on our two objects. So let's just look at the free body diagram for these two objects. So free body diagrams, just so we can see all the forces acting on our objects. So the free body diagrams for the table and book combo. So for the above example, we have the book. Quickly try and redraw it. Where we got our book, and there's two forces acting on this. We have the normal force pushing up on the book in what we might call the positive y direction. And then we have the weight pulling the book down, right? The weight of the book, which we call W sub b. And that has a magnitude of mg. So we also have the table, right? Let me just try and very quickly draw the table again. One of these, one of these. Right, maybe something like that. So notice that at each point that the leg of the table touches the ground, right? So we got 4 legs to this table, and each are in contact with the ground. So because of that, there's going to be 4 normal forces. So it's going to be the normal force of the first leg touching the floor, second leg touching the floor, so on and so forth. 1 for every leg. So I call this Fn1, Fn2. Right, so we just have a bunch of normal forces. This will be 3. This one will be 4. Right. Actually, maybe I shouldn't put this one here. Let me move this over right here. Very good. But those aren't the only 2 forces acting on the table, right? The table itself has a weight, which means, that force, the weight, is going to be pointing straight down towards the center of the Earth. So the weight of the table is going to be equal to, the mass of the table times gravity. And for the book over here, should probably label this, it's going to be the mass of the book times g. Right. But in our physical example, right, we have that the book is resting on the table. So not only does the table have to support its own weight, it also has to support the weight of the book. And so I'm going to draw that slightly off center. It kind of looks like this. And maybe I'll draw like this. So there's also the weight of the book to consider. So you have to be very conscious of all the forces acting on an object whenever you're trying to break down these problems into their components. So this is just a little diagram, a little example of how we would analyze a situation like this, right? How would we apply all the forces? But we're not really going to do much more with that since we're not dealing with specific numbers or anything like that. So let's move on. So next I'd like to talk about apparent weight. So the apparent weight of an object, right? If you've ever ridden a roller coaster or ridden on an airplane that suddenly descended too quickly, you might have experienced apparent weight. So imagine that you're in an elevator in a very tall building, and this elevator is known to accelerate, up or down with some acceleration A. So if we were to step on a scale while riding the elevator, what would the scale show? What would our apparent weight be according to this scale? So for our apparent weight, just like that. So we're going to first stipulate that we're going to determine the weight by a scale. We determine the weight by a scale, right? And next up, we can ask the question, well, what if we are on the scale and accelerating? So what if we are on the scale and accelerating? Right, so this is similar to the question that I just asked. So in this case, the scale will show the magnitude of our normal force. All right, so let's sort of see what I mean by this. So let's suppose that we are in an elevator. All right, we got this elevator which looks like this. Right, and at the very bottom of the elevator, there's a scale. And we are standing on the scale. There we go. So this thing is a scale. Right, we can look at the number on the scale and it'll tell us our weight, or at least our apparent weight. And so we're inside an elevator. And so we're inside an elevator. Right, and this elevator might be accelerating up or down with some acceleration A. So according to the free body diagram of this problem, right, the two forces acting on us, standing on this scale, are the normal force going up, right? It's the force of the scale pushing up on us. And pointing in the opposite direction, we have our weight, which is just mg. Right, and this whole thing is accelerating with some acceleration A. So let's look at this. So in the x direction, right, when we add up all the forces in the x direction, right, you take all the forces in our problem, you break them down into their x and y components, and you add all the x components together. You'll notice that, well, none of our forces are pointing in the x direction, right? They're all pointing in the y direction. Right, these are all pointing in the y direction. So none of our forces have x components. So when we add all of the x, forces up together, we get 0 newtons in the x direction. Right? And so we know, according to Newton's second law, that since there is no net force in the x direction, there will be no acceleration of us in the x direction. Now the y direction is a little bit different, right? Because now when we add up all the forces in the y direction, right, we break all of our forces into their x and y components, we just add their y components together. Well, that's not going to be 0, right? That's going to be equal to our mass times our net acceleration in the y direction. But our net acceleration in the y direction is given by the acceleration of our elevator. Right? So we have, breaking this down a little bit more. So on the left-hand side, we have the sum of our forces in the y direction? Well, we have our normal force pointing upwards in the positive y direction. So we say that it's positive. We have Fn. And then we have our weight pointing down in the negative y direction. So we say that it's negative, so minus W. So that's going to be equal to our mass times our acceleration in the y direction. Maybe I'll just put it like that. Right? Or actually, I'll just leave that off, since our acceleration in this case is entirely in the y direction. So we know that our weight, at least the magnitude of our weight, is given by mg, right, where g is just 9.8. 9.8 meters per second squared. All right, so on the left-hand side, we have our normal force minus our weight. On the right-hand side, we have our mass times our net acceleration. So if I add mg to both sides, we get that our normal force, right, the thing that will show up on our scale, is going to be equal to our mass times our net acceleration plus our mass times the acceleration due to gravity. And we can actually factor that mass out because it's the same. So we see that our normal force that the scale would show, upon riding in this elevator, is equal to our mass times how fast how fast the elevator is accelerating, plus the acceleration due to gravity. Right? So notice that if the elevator is not accelerating, right, maybe it's just going up or down at a constant velocity, then our A would be 0. And so if this is 0, then the scale would just show our weight, which makes sense. So notice that if our acceleration is positive, right, if we're going up, if we're accelerating upwards, so A is a positive number, then we have this number, which is going to be positive, plus our weight, which is also positive. So our scale is going to be some number, some positive number, plus our weight. So our apparent weight, in this case, is going to be heavier than if we were not riding in this elevator. Right? And likewise, if now we're instead accelerating downwards, so our acceleration is negative, we would have our weight. We would have our weight minus this term, since our acceleration is now negative, and our apparent weight that would show up on our scale would be smaller than our normal weight. That's why we feel so weightless when we're going downwards on a roller coaster or when our plane suddenly descends, right? Because, our roller coaster / plane / elevator is accelerating downwards. So let me just actually write that off. So we have our apparent weight. It's going to be equal to our weight plus the mass times the net acceleration of our object. So I'm going to box that off. So Fn is the normal force, but it's also our apparent weight because that's what the scale is registering. And mg is just our weight. So let's look at an example. So example 1. So for our first example, just scroll down a little bit. So for our first example, it says that a person is standing on a scale. Person is standing on a scale. Inside an elevator. Problem goes on to say that her mass is 150 kilograms. Her mass is 150 kilograms. And the question is asking, well, what number will the scale show? What number will the scale show if the acceleration of the elevator is part A. The acceleration is all in the y direction, and it's accelerating upwards at 5 meters per second squared. Part B is asking, well, what if the acceleration in the y direction is 9.8 meters per second squared? Now we're accelerating upwards at 9.8 meters per second squared. Part C is asking if now we're accelerating downwards at minus 9.8 meters per second squared. And yeah, no, that's it. Okay, so there's 3 parts to this problem. Well, let's just write down our apparent weight. So Fn is equal to our weight, mg, plus our mass times our net acceleration. So in this case, we're only accelerating in the y direction, so just keep it like this. Like I mentioned before, we can factor this mass out since it's the same for both. So this is going to be acceleration due to gravity g plus a. And so now we're going to plug in our values. So for part A, we're accelerating upwards at positive 5 meters per second squared. So the normal force that we'll show, right, the apparent weight on our scale is going to be our mass, which is 150 kilograms, times the magnitude for the acceleration due to gravity. It's going to be 9.8 meters per second squared, plus our acceleration for the elevator. So it's 5 meters per second squared. Right. So when you add these up, you get an apparent weight, right? An apparent weight of 2,220 newtons. So this is the answer to part A. Part B. Part B says now we're accelerating upwards at 9.8 meters per second squared. So our normal force slash our apparent weight in this case is going to be, going back to this formula, we have our mass of 150 kilograms times positive 9.8 meters per second squared, plus the acceleration of our elevator, which in this case is again positive 9.8 meters per second squared. So this is going to give us 2,940 newtons. Right, so our apparent weight that our scale shows is just this. And last but not least, for part C, wants us to figure out the apparent weight the apparent weight if our acceleration in the elevator is minus 9.8 meters per second squared. So our elevator is basically in free fall with us inside of it. So it's accelerating downwards at minus 9.8 meters per second squared. So according to this, our apparent weight is our mass, which is 150 kilograms, times 9.8 meters per second squared, plus our acceleration, but that's going to be minus 9.8 meters per second squared. So see that we have 9.8 minus 9.8. So the thing in the second set of parentheses here is going to be 0. So our apparent weight is going to be 0, right? If we were in that elevator, we would be experiencing weightlessness. Right? Our scale it would show that our weight is 0 if we were standing in that elevator on that scale. All right, so that's it for that example. So next up, I'd like to discuss static and kinetic frictional forces. So static and kinetic frictional forces. Right. So these forces occur whenever there is contact between two objects, and we're not neglecting friction, right? Sometimes during physics problems, we pretend like friction isn't there, like, for example, if we're sliding on ice, but that's just an assumption we include in our problem. In real life, there is friction everywhere. Friction is a force, which is why we are talking about it in the first place during this lecture, but that means that it has a magnitude and a direction. So for the direction part of the frictional force, that's going to point in the direction opposite the actual or intended motion of the object. So to begin with, we're going to look at the static frictional forces. So as a quick example, if we have a box, it's like this, right? And we're applying a force this way, and there's friction and a problem. So, I haven't specified what's causing this force F on this box, but because we have this force F, the box wants to accelerate to the right in this case. And because of that, our frictional force will be pointing in the opposite direction. So if you remember, we indicate frictional forces by lowercase f. And likewise, if the box, right, the force we're applying to the box is somehow in the opposite direction, like over here, then the frictional force is going to be pointing, it's going to try and oppose that motion, right? The box in this second case wants to move to the left. So the frictional force is going to be pointing in the other direction, right? So to begin our talk of frictional forces, we're going to first talk about static frictional forces. So static frictional forces. So I'm just going to write down how we figure out the max magnitude for the static frictional force. So we have, let me zoom in a little. So we have that the max value that our static frictional force can take, I'm going to call it F sub s max. This is going to be equal to our coefficient of static friction, which we denote by mu sub s times our normal force. Right, well, times the magnitude of our normal force. So this thing right here is called mu, right, mu, and it is our coefficient of static friction. And as a side note, it has no units. Right? So our static frictional force is a force, and that's equal to this coefficient times the normal force. But you'll notice that this force right here, this normal force, it already has units of newtons. So this can't have any units, because otherwise then our static frictional force also won't have units of newtons, which we want it to. All right, so S here stands for static. So S stands for static. The reason why we have max is because the magnitude for a kinetic frictional force is going to be less than the magnitude for a static frictional force. right? So this indicates that the most force a static frictional force can generate is equal to this coefficient times our normal force, right? If we exceed this amount of force, right, if our net force, if we push on an object hard enough to overcome this static frictional force, then our object is going to start moving. And in that case, we're not dealing with a static frictional force, we're dealing with a kinetic frictional force, right? We call them static frictional forces because the word static tells us that we're not moving. So this is in contrast to kinetic frictional forces, which are the frictional forces between objects in motion along a surface and that surface itself. So static implies stillness, kinetic implies motion. So let's work out an example using static frictional forces. So this is going to be example 2. So example 2. Keep that in the frame a little bit. So example 2 says a box of weight or of mass 20 kilograms. So a box of mass 20 kilograms is on a surface. It's on a surface with a coefficient of static friction between the box and the surface of 0.8. Remember, no units. So the problem wants us to find the magnitude of maximum force. So find the magnitude of maximum force that can be exerted horizontally in the box, that can be exerted horizontally on the box without moving the box. Right. So let me just draw our lovely box. You'll notice that this section will have a lot of boxes in it. Got a box that looks like this. So I'm going to draw the forces coming from the center of the box. So we have a force of the floor pushing up on the box. So our normal force. We have the weight of the box pulling the box down in the negative y direction. So the weight of the box, mg. So we're pushing on the box with some force to the right, horizontally. We're going to call this force F. So it's going to be in the positive x direction. And then there's going to be some static frictional force that's going to be preventing the box from moving. So that's going to be max force, the max static frictional force, right? So we're going to use the component version of Newton's second law to try and help us out here. So first, we're going to look at stuff in the y direction. So to begin with, when we add up all the forces in the y direction, it's going to be equal to, right, the mass of our object, the mass of our box, times the net acceleration of the box in the y direction. So let me ask you guys this. What should our acceleration in the y direction for this box be? Right? We just want this box to slide along to the right, for example. But realistically, we actually don't want this box moving at all. Right? But this problem is actually asking for, like, how hard can we push on this box horizontally without moving the box? So we don't want the box to move. So if the box is initially at rest, right, in both the x and y directions, which I'll just denote by V naught is equal to 0 meters per second, right? If the box is not initially moving, then if we don't want the box to move, that means its velocity can't change. So in that case, that means that our acceleration for both directions, in this case, has to be 0. So in the y direction, it has to be 0 because we don't want it accelerating upwards, right? We don't want it floating up, and we don't want it sinking into the ground. So the right-hand side of this is 0 newtons. And so looking at the sum of the forces in the y direction on the left-hand side, right, you have the normal force pointing in the positive y direction, so we'll say that it's positive. And then we have the weight pointing in the negative y direction, so we say that it's negative, so that's going to be minus our weight. And so it's going to be our normal force minus our weight, which has a magnitude mg. And this is going to be equal to 0, right? Because the right-hand side of this is 0. So we can add the weight to both sides to get that the normal force needs to be equal in magnitude to the weight of the box if we don't want it accelerating up or down in the y direction. So this is going to be one key result. Okay. Now let's look at stuff in the x direction. So similarly, when we add up all the forces in the x direction, that's going to be equal to the mass times the net acceleration of our box in the x direction. But again, because we don't want the box to move, right, we don't want its velocity changing, the acceleration in the x direction also has to be 0. So the whole right side of this equation is going to be 0. So looking at a little diagram up here, in the x direction, we have the force that we're pushing on the box with. In the positive x direction, so we'll say it's positive. And then we have this static frictional force pointing in the negative x direction, so I'm going to make that negative. So that's why we use a minus sign there. And that's all equal to 0. So what I'm going to do, I'm going to add this to both sides to get that the max force that we can push on this box with without getting it to start moving is equal to the magnitude for the maximum value for our static frictional force, right? Which we know to be equal to the coefficient of static friction times our normal force. But in this part right here, we just figured out that the normal force is mg. So then the most force we can apply horizontally to this box without moving it, in this case, is going to be equal to our coefficient of static friction times the mass of the box times the acceleration due to gravity g. Right. So according to this problem, the hardest that we can push on this box is the coefficient of static friction, which is 0.8 times the mass of the box, which box has a mass of 20 kilograms. Right, and the acceleration due to gravity is 9.8 meters per second squared. So we see that when we multiply all this together, we get that the most amount of force we can apply horizontally to this box without making it move is 156.8 newtons. 156.8 newtons. So that's the answer to our problem. So now let's talk about kinetic frictional forces. So kinetic frictional forces are pretty much defined in the same way as static frictional forces. Right, the only difference now is that our object is actually moving. So for our kinetic frictional force, we have that the magnitude for our kinetic frictional force, which we denote by F sub k, right, for kinetic, that's equal to the coefficient of kinetic friction between our object and the surface that it's sliding along, times the magnitude for our normal force. So this is important, so I'm going to box it off. There we go. So our kinetic frictional force, so K in this case, like how in the previous part S stood for static, K in this case stands for kinetic, right, or moving. And again, this mu sub K stands for the coefficient of kinetic friction. And again, it has no units. So I actually want to go back and touch on something real quick. So for the static frictional force, I forgot to box off. Let me just do that real quick right now. So for a static frictional force, right, the magnitude of this force is proportional to this normal force. Right. So what does that mean? Intuitively, right? If you try to push, let's say, a bookshelf full of books in it, if you try and push that bookshelf across a carpet, and right, it's full of books, you're going to have a harder time pushing it than if there were no books in it at all. Right. The reason for that is because if we look at a free body diagram of our bookcase, right, this is a zoomed out version, but you'll have the normal force, right, and this is without it moving. You're going to have the normal force of the ground pushing up on the bookcase, and then you're going to have the weight of the bookcase pulling down. And if you look at the sum of the forces in the y direction, that's going to be equal to the mass times the net acceleration of our bookcase in the y direction, right? But we don't want our bookshelves, you know, unless we live in a haunted house, we don't want our bookshelves floating up, right? We don't want them accelerating upwards, and we don't want them sinking down into the floor. So the right-hand side of this has to be 0 because we don't want our bookshelf to start moving in the y direction. So on the left-hand side, that just equals the sum of our forces. So in that case, we have the normal force pointing in the positive y direction, and then we have the weight pointing in the negative y direction. It's equal to 0. So our normal force has to be equal and opposite in magnitude to our weight. Right? So what this is saying is the heavier the bookshelf, the greater the value for our normal force, but the larger our normal force is, right? The larger the force of, you know, the ground pushing up on the box, the more frictional force we experience, right? Because we have more normal force being applied by the ground. Right? So this is why it's harder to push a bookshelf full of books in it as opposed to if the bookshelf did not have any books in it. Because without the books, the bookshelf should weigh a lot less. And therefore, the amount that the floor is pushing up on the bookshelf should be less, right? This normal force should be less. And therefore, the amount of static or kinetic frictional force that we're experiencing should also be less. So that is a little bit of a little side note, but I felt like it's good to explain. Okay, so let's look at an example using kinetic frictional forces. So this is going to be example 3. So example number 3. New and improved with kinetic frictional forces. So example 3 says that a person is pulling a 50 kilogram box. 50 kilogram box on a surface with a coefficient of kinetic friction equal to 0.2. So the force has the magnitude. So the force has a magnitude of 200 newtons. And is directed (30 degrees) above the horizontal. So above the positive x-axis. So the problem wants us to find the normal force pushing up on this box. Wants us to find the kinetic frictional force, at least the magnitude of the kinetic frictional force, F sub k. And it also wants us to figure out what the acceleration of this box is in the x direction. So it wants us to find these three things. Very good. So we start by drawing a picture. So we have floor, we've got our box. So as always, I'm going to pretend like our forces are starting from the center of the box, just because it's easier to draw. So we have the normal force of the floor pushing up on the box. You have the weight of the box pulling it down. So this is the weight, mg. Then you have some dotted lines here. So you have some force F being pulled off like this. So force F, and it's got a magnitude of 200 newtons. It's being pulled at an angle 30 degrees above the positive x-axis. And since our box is being pulled, to the right, the kinetic frictional force is going to oppose that motion and is going to be pointing to the left. There we go. So this is our kinetic frictional force. All right, now, so part A, we again note that there is no motion along the y-axis. Right, the initial velocity of this box in the y direction is 0, and we want it to stay 0. So this implies that our acceleration in the y direction has to be 0, right? We can't have this thing accelerating upwards or downwards. So looking at Newton's second law, for the y component stuff, we see that when we add all the y components for our forces together, it's going to be equal to the mass times the net acceleration of our box in the y direction. But we want this net acceleration in the y direction to be 0. So the right-hand side is 0. So now we need to take this force, F, and we need to break it up into its x and y components. So force F, for the x component, that's going to be equal to its magnitude of 200 newtons times cosine 30 degrees. So it's going to give us our x component for this vector F. And for the y component, it's going to be 200 newtons, right? Its magnitude times sine of 30 degrees in the y direction. So actually punching this into a calculator, we get the x component is 173.2 newtons. Oh, let's just call it 173 newtons. I don't feel like dealing with the decimal points. And in the y direction, this is 200 newtons times sine of 30 degrees. So this is going to be 100 newtons in the y direction. Right? So going back to Newton's second law in the y direction, this equation right here, we have the sum of our forces in the y direction. So if we look, there's 3 forces here that have components in the y direction. There's our pulling force, F. There's the normal force pointing in the positive y direction. Then we have the weight, which is pointing in the negative y direction. So we have the normal force pointing in the positive y direction. We have the component of our pulling force F in the y direction. So that's pointing up. So that's plus 100 newtons. And then last but not least, we have our weight, which is pulling down in the negative y direction. So we put a minus sign. So it's minus our weight. And all of that is equal to 0. All right, so now what we can do, right? So part A is asking us to solve for the normal force. So what we can do is we can add the weight mg to both sides and then subtract off 100 newtons. And so when we do that, we get that the normal force is equal to mg minus 100 newtons, right? But we know that the mass of this box is 50 kilograms. This is 50 kilograms divided by g. So this is 9.8 meters per second squared minus 100 newtons. So when you punch all this in, we get a normal force, the ground pushing up on the box, a normal force of magnitude 390 newtons. All right, so this is part A. Now part B wants us to figure out the magnitude for our kinetic frictional force, but that's not too bad because the magnitude for our kinetic frictional force is going to be equal to the coefficient kinetic friction times the magnitude for our normal force, but we just found that. So the magnitude of our normal force. So we see that the magnitude for our kinetic frictional force is the coefficient of kinetic friction, which is 0.2, multiplied by our normal force magnitude, which is 390 newtons. Right? And when you punch this in, we get a kinetic frictional force magnitude of 78 newtons. Like that. Right. And last but not least, part C is asking us to find the acceleration of the box in the x direction. But we can do that by solving for Newton's second law in the x direction. So the sum of the forces on the box in the x direction, that's going to be equal to the mass of the box times our acceleration in the x direction. Now, if we go back up to our picture, we notice that there's really only two forces in our problem that have x components. There's the pulling force that we're applying, and then there's the kinetic frictional force, which is pointing in the negative x direction. So we see that the x component for a pulling force, we found that to be 173 newtons. So on the left-hand side, we have 173 newtons in the positive x direction, and then we have minus, right, our kinetic frictional force here. Right, it's negative because it's pointing in the negative x direction. Well, it's minus 78 newtons. This is going to be equal to the mass of our box, which is 50 kilograms, times our acceleration of this box in the x direction. So solving for the acceleration, right, if I just divide both sides by 50 kilograms, we get that the acceleration of the box is equal to 1.9 meters per second squared. Like that. And with that, we have solved for everything this problem is asking us to do. So next up, I want to talk about tensions. So the tension force. So the tension force. Right. So tensions arise when you're pulling on a rope or a wire or something like that. And so if we have, for example, a box, right, there's going to be a lot of boxes in this course. So you're pulling on a box with a rope. Maybe I'll show the rope in brown. Right. So maybe we've got some rope like this. It's going off. So if we pull at the end of this rope, for example, and we pull to the right with some force F, and what's going to happen is that force is going to be translated down the rope to our box. So what's going to end up happening is the force on the box right here is going to be the tension in our rope. So rope. Right. And it's about as simple and as complicated as that. So let's look at an example to sort of get used to this idea. So we have example 4. So example 4. So example 4 says that find F such that the box does not move. Such that the box does not move. And there's a picture associated with this, so I'll draw that. I'm going to go down a little bit. So up here, we have the ceiling. So I'm just going to attach this like that. So that's the ceiling. And from the ceiling, we have pulley, or just like a little frictionless thing for the rope to slide over. And then we have the rope dangling off one side like this, right? And we're pulling downwards on this with some force F. So that's the force F in this problem. So it's asking us for the magnitude such that a box that's being suspended on the other side of this pulley system by this rope, like this. We want this box to not move. So let me draw the forces on this box. So on the top of this box, we have the tension, right, pulling up. And then, we have the weight of this box pulling down. So let me switch colors, I guess, to blue. So we have the weight of the box pulling down, right, with this mg. Just like that. So let's look at the free body diagram, just for the box, for example. So looking at the box, we got two forces in the y direction. We've got the tension, and we've got the weight, mg. Right? So we don't want this box to move. So because of that, when we look at Newton's second law, while looking at this box, right, we look at all the forces in the y direction, we add them together. We want that to be equal to the mass of the box times the net acceleration of the box in the y direction. Now we don't want this box to move, so the acceleration has to be 0 in the y direction, and incidentally also in the x direction, but we only care about the y direction for now, because this box can really only go up or down for our problem. So on the right-hand side, we want this to be 0. And on the left-hand side, we have the sum of our forces acting on the box. Well, we got two forces. We have the tension pulling up and the weight pulling down. So we have the tension T pulling in the positive y direction, and we have the weight mg pulling in the negative y direction, so it gets a minus sign. So all that is equal to 0, right? And now if we add mg to both sides, we get that the tension in the rope, if we don't want this thing to move, the tension in the rope has to be equal to mg. Right? But notice how on the other side, we have this downward pulling force on the box, right? We're applying some amount of force to this rope. So I would like to point out an important feature of pulleys, right? Whenever you see a pulley in a problem, the only thing that a pulley does is it redirects the force. So really what we have is we have the rope starting at the box, goes around the pulley, and then it just goes down where we are pulling on the rope. right? So when we pull down on the rope, the box goes up. So the more force we pull down on the rope with, the more force the box feels going upwards. And in our case, the way that we represent this with equations is that the magnitude of the force that we apply to this rope on the other side, right, the magnitude of this force, F, has to be equal to the magnitude of our tension T, right? Because the harder we pull on this rope, the more tension there is in the rope, and the box will accelerate upwards when we accelerate the rope downwards. So if F is equal to T, this says that if we don't want the box to move, then the most force that we can apply, or actually not even the most, the exact amount of force that we need to apply to this rope in order for this box not to move is equal to mg. So that's it for this little example. So tension problems aren't really too different from anything that we've seen before. They just involve like ropes and wires and stuff like that. So next, I'd like to talk about equilibrium applications of Newton's laws of motion. So let me go down. So the next section is called equilibrium applications of Newton's laws of motion. Newton's laws of motion. I know it's getting a little cramped, but that's okay. All right, so what do I mean by equilibrium? So in equilibrium, this means that an object is in equilibrium when it has zero acceleration, has zero acceleration. Right, that is, the x component for our acceleration is 0, and the y component for our acceleration is 0. Just like that. So because of that, right, if we look at Newton's second law in component form, for the x component stuff, we see that when we add all the x components for our forces together, that's equal to the mass times the net acceleration in the x direction. And for the y component stuff, when we add all the y components for our forces together, that needs to equal the mass of our object times the net acceleration in the y direction. But if our problem is an equilibrium problem, our accelerations are 0. Right? Our net acceleration is 0, which means that for an equilibrium problem, the sum of our forces in the x direction are 0, and the sum of our forces in the y direction are also 0. So let me move this over a little bit. Right, so the sum of our forces in the y direction are also 0. So these are the two conditions for an equilibrium problem. So let's see an example. So this is example. Oh man, what example is this? Example 5. All right, so example 5 says that the helicopter in the drawing, and I'll show you what I mean, but the helicopter in the drawing, which I'll draw later, is moving horizontally to the right, is moving horizontally to the right at a constant velocity v. At a constant velocity v. Right, so this is an example of an equilibrium problem because if the acceleration, or excuse me, if the velocity is constant, that means there's no acceleration. And if there's no acceleration, it's an equilibrium problem. So the problem says that the weight of the helicopter, is a lot. So the weight of the helicopter is, or at least it has a magnitude of 53,800 newtons. So the problem says that the lift force L, and this is just a regular force, that there's nothing special about it. So lift force L generated by the rotating blade, makes an angle of 21 degrees. Makes an angle of 21 degrees with respect to the vertical. So that's important. With respect to the vertical. So what is the magnitude of the lift force? So part A says, what is the magnitude of this lift force? Part B says, determine the magnitude of the air resistance. Determine the magnitude of the air resistance R that opposes the motion. So that's the problem. All right, so I can't draw a helicopter, but I can draw the free body diagram for this situation. So let me just zoom out a little bit. I'm going to draw the x-axis, the y-axis, the x-axis, just like that. This is the y-axis up here. And so what this thing is saying is that we've got a couple of forces. So we have the lift force, which is pointing up like this. This is our lift force L. The problem is telling us the angle between the vertical axis and our lift force is 21 degrees. So we're going to have to deal with that later. Up next, we know that the weight of this thing is pointing downwards towards the Earth. So this is the weight. And then, last but not least, we have some air resistance. Backwards, you can think of this as like a, I don't know, kinetic friction if you like. So that is just some force pointing in the opposite direction. All right. So part A wants us to figure out what the magnitude of this lift force L is. So that's not going to be too bad. So first things first, what we need to do is we first need to find the angle between our lift force and the x-axis. So we need to find this angle, not necessarily this 21 degrees. So we know that between the x-axis and the y-axis, right, that whole angle is 90 degrees. And then if we go backwards 21 degrees, you get that 90 degrees minus 21 degrees gives us the angle between our lift axis, or gives us the angle between our lift force and our x-axis. So in this case, this is going to be 69 degrees. Nice. So we need to break up. So we need to break up our lift force into its x and y components. So to do that, I'm going to write that the x component for lift force is equal to its magnitude, which I'm just going to call capital L, right? Where capital L is just the magnitude, right? So it's L times cosine of 69 degrees, and the y component for our lift force is L times sine of 69 degrees. So the x component for our lift is going to be L times cosine of 69 degrees is about 0.358. 0.358. And for now, since we don't know what L is, it's the thing we're looking for, we're just going to have to leave it as is. So the y component for our lift force is the magnitude L times sine of 69 degrees, which is about 0.934. And so now that we have that broken up to its x and y components, we can continue on with the problem. So a good place to start is by looking at the y direction. So this is an example of an equilibrium problem, right? So we want our x and y acceleration components to be 0. So if we're looking at stuff in the y direction, we have that some of the forces in the y direction are equal to the mass of the helicopter times the acceleration due to gravity, or times our net acceleration in the y direction, excuse me. And we know that this is going to be equal to 0. So left-hand side, we have the sum of the forces in the y direction. So we have the y component for our lift force. And in the negative y direction, we have the weight of the helicopter pulling us down. So in this case, we have the y component pointing the positive y direction minus the weight of our aircraft. That's going to be equal to 0 newtons. So now I'm going to add the weight to both sides, and we're going to get that the y component of our force, lift force, is going to be equal to our weight, right? Which, according to the problem, was 53,800 newtons. Just like that. But the left-hand side, right, we found it to be the magnitude L. Right, so the y component of our lift force is equal to the magnitude of the lift force, L, times sine of 69 degrees. That is about 0.934. Right, that makes up the left side. So on the right, we have 53,800 newtons. And if we divide both sides by the 0.934, we get that the magnitude for our lift force is equal to 57,627, roughly. So that's part A. Now part B is asking us to determine the magnitude of the air resistance R that opposes the motion. So now if we're looking at stuff in the x direction, so the sum of forces in the x direction, it's going to be equal to the mass of the helicopter times the net acceleration of this helicopter in the x direction, right? But if our helicopter is flying to the right at a constant velocity, that means it can't have any acceleration in the x direction. So on the right-hand side of this equation, this is again going to be 0. And so on the left-hand side, we have the sum of the forces. And there's only 2 forces in this problem that have x components. Right, there's the x component of L, which we found to be this. And then there's the resistance from the air, which we call R. So the sum of the forces in the x direction, we have the x component for our lift force, right, pointing in the positive x direction, minus the air resistance R, which points in the negative x direction, so it gets a minus sign. And so all of that is equal to 0. And so if we add R to both sides, we see that the x component for our lift force has to be equal in magnitude to the air resistance, right? So again, we're trying to find R, trying to find that. So we see that R is equal to the x component for our lift force, but the x component for our lift force is just the magnitude of the lift force times, what is it, cosine of 69 degrees. So it's going to be L times 0.358. 0.358. Right. But we just solved for L. So we get that R is equal to 57,267 newtons, or 627 newtons, excuse me, times 0.358. And when you multiply all this together, you get an air resistance magnitude. So the magnitude of this air resistance R is 20,651 newtons. 20,651 newtons. Just like that. So that's the answer to the second part of our problem. So for the final part of our lecture today, I'm going to talk about non-equilibrium applications of Newton's laws of motion. So non-equilibrium applications of Newton's laws of motion. Right. And this section is incredibly short, right? So in non-equilibrium cases, this just says that if you add up some of the forces in the x direction, this can be equal to the mass times your net acceleration in the x direction. And when you add up all the y components for your forces in a problem, right, on an object, that's going to be equal to the mass of the object times your net acceleration in the y direction. And so what the non-equilibrium case for Newton's laws of motion is telling us is that these, at least one of these accelerations, are not zero. Right. So either AX is not zero, or AY is not zero, or both AX and AY are not zero. Right. So the reason why it's called non-equilibrium is because one of these accelerations is not zero. And so we're going to see examples of non-equilibrium applications of Newton's laws of motion in the Thursday class, where we are, working a whole bunch of problems. We'll do plenty of those at that time. So that's all I have for you guys today. If you have any questions, I'll be more than happy to answer them. But otherwise, I will see you guys tomorrow.